ATAL FDP online program. So I welcome our today's expert, Professor Dipti Ranjan Sahu. In short, I will introduce Sir. Sir is a professor in Department of Civil Engineering, Indian Institute of Technology, Delhi. His professional focus is basically expertise in earthquake engineering, performance-based design, seismic design, passive vibration control, real-time hybrid testing, and simulation, nonlinear finite element analysis, seismic retrofitting and strengthening, structural fire engineering, concrete, steel, and composite structures, cold form steel, and fiber reinforced concrete. Sir has done his PhD and MTech from IIT Kanpur. He has received a number of awards, prestigious awards like Life Fellow in Institution of Engineers, India, Outstanding Reviewers Award by Construction Building and Materials Elsewhere Science, Outstanding Reviewer by Structures Journal Elsewhere Science, Outstanding Reviewer by Engineering Structures Elsewhere Science, and he has also received Young Associates, Indian National Academy of Engineering, India, Young Engineers Award by the Institution of Engineers, India, Young Engineers Award by Indian National Academy of Engineering, India, Young Scientist Research Award by Department of Atomic Engineering, India, Young Scientist Award by Department of Science and Technology, DST, India, Outstanding Employee Certificate Award, and the various other awards are received by the Professor Sahu. His contributions in the form of he has published the number of patents and the referred journals and the conferences and the book chapters, etc. He is a member of various professional bodies and the member of various reviewer committees, and also has given the various expert talks in the national and international levels, and various he is also carrying out the consultancy works and etc. On behalf of Civil Engineering Department, University Institute of Technology, RGPV Bhopal, and from the AICT ATAL program, I welcome you, sir.
Thank you, Dr. Rawat, for this introduction. So I think I have two lectures back to back. And so I'll start with the first one. I hope my screen is visible to all.
Yes, sir. Yes, sir. It is visible.
Okay, so the first lecture is on earthquake resistant design. Mostly I'll talk about the concepts and the practices, like what is being followed right now in the Indian context. And at the end of this lecture, I would be happy to have a interactive session. So I expect some questions, although some of the topics I may not cover because of the lack of the time. So the idea is to explain what are the concepts of the earthquake resistant design, and mostly I limit my presentation to IS 1893 2016 and IS 13920 wherever it is possible. These are the latest codes as far as the detailing and the design for the earthquake resistant structures are concerned in India. So we know that the concept of earthquake resistant design is little, I will say that it is qualitative in nature. Qualitative in the sense we can't predict the earthquake when it would occur and what magnitude it would be. So sometimes it's it can be a very big earthquake, or it can be minor shaking. So the most of the earthquakes are actually not frequent, and if you want to design a structure without any damage, that would be highly expensive in nature. So as a structural designer, what we want to do is we want to actually compromise between the cost and looking at the uncertainties involved in the occurrence of the earthquake. And since the earthquakes actually have a different intensity, right? It can be very, very minor to very, very severe earthquake. So the initial thinking, or most of the codes, including our code currently, there are some understanding of how to take care of the earthquake load, which is mostly, or maybe the damaging effect is mostly related to the lateral direction of the loading. It has been qualitatively defined as the minor shaking, moderate shaking, and the severe. So when I say the minor shaking means, like, there are small, small earthquakes which are very frequent. And when I say the severe earthquake means there are big earthquakes and which are probably like not that frequent as compared to the minor earthquake. And in between there would be moderate shaking. Now, if you ask me that what is the magnitude we're talking about, the minor earthquake and severe earthquake, as such, they are not somewhat directly related to the magnitude of earthquake. It is all how damaging the earthquake is. So it's essentially mostly related to the intensity of the earthquake. So when I say the intensity of earthquake means, like, a 6 magnitude of earthquake can be more intense in damaging the structure depending on the site conditions and the localities, like kind of infrastructure you have, as compared to like a magnitude of 8. If actually the magnitude of 8 earthquake actually occurs like in a remote area where there is no infrastructure, no buildings, bridges, probably that would be not that severe for the design as compared to a 6 magnitude or 7 magnitude earthquake in a very highly dense populated area. So with the understanding of this, what the objective, design objective is actually framed, not in India, in many of the countries actually, worldwide, that if you have a minor shaking, there should not be any damage to the structural and non-structural component. What is this, the meaning of structural components? Means that is the primary elements which actually resist the loading or transfer the loading. For example, you can say, beams, columns, to some extent slabs also. And at the same time, you have the non-structural elements, for example, the glass panels. Sometimes the infill walls actually, we don't design to be structural elements if it is actually put it in the infill RC frame, because in the reinforced concrete frame, we rely on the behavior of the beams and columns to transfer the loads. So you have both the elements are there in a structure, like structural and non-structural elements. So the idea is, since these are the frequent earthquakes and minor or very small earthquakes, which have probably like the kind of demand it imposed on the structure is very, very low. So the idea is my design should be capable of, uh, giving me the no damage to the structural and non-structural components. In case of the moderate earthquakes, so idea is there should not be any structural damage, but I can afford for the non-structural damage. For example, my beams and columns probably should not damage to that extent that it will lose its capacity to resist the lateral loads or the gravity loads, and but I can allow my non-structural components to get damaged, so that after the earthquake, I only thing I have to change is probably the facades or the glass panels or the infill walls, like this. Severe earthquake, which you call as the big earthquake, which are very, very infrequent, because mostly these kind of earthquakes are actually doesn't occur like a span of 20 or 30 years. It might be very long return period. Uh, so in this case, because this is once a while, the idea is the structure may damage but not collapse. So inherently, that what you are saying, that here your non-structural and structural damage will be there, but there should not be any collapse of the structural components. So this is essentially the objectives of earthquake resistant design in many of the codes. What is the design implications? Implication is like whatever the design load you estimate, that should be less than the maximum expected capacity of the structure. And here what we mostly rely on the inelastic response of the structure. So earthquake design, or although our design is elastic, the expectation is that if that element goes to the damage is always inelastic term. So if it is damaged, it should have sufficient capacity to resist the load. It should have sufficient capacity to provide you the deformability, energy dissipation, etc., and damping. Now, how do we protect the structure from being damaged or not being collapsed? So we actually need to put or ensure that if I'm designing for an earthquake loading, there are some detailing I have to do, and also at the same time the construction quality need to be improved. At the same time, in a locality there are different types of the structures. Like some of the structures require the high level of protection. For example, like your hospital, your probably like electrical substations. So these are the called as the essential facilities. And maybe you might have the dams, the nuclear power plant, and at the same time you have the residential structures, like where the occupants actually live. So if we see that, probably like one can see that, like if out of these three types of structure, which is called as the general ordinary facility, essential facility, and the very, very critical facility, this is the dams and the nuclear power plants. So probably like as a designer, I should ensure that the dams and nuclear power plants should be the last one to get damaged, followed by like your essential facilities, and probably the first level of like, or the probably the least level of protection I need for the residential structures, because as a whole the society would be highly affected, but the casualties will be more if your very, very critical structures get damaged or the essential facilities get damaged. So just before going to the design concept, it's important to understand what are the basic differences between the wind loading and earthquake loading. So wind loading is mostly oscillatory in nature, and they are, probably we take it, kind of a monotonic loading. That means in one-way loading, you apply the structure in one unidirectional. Whereas the earthquake loading is random, it's dynamic, and at the same time it is cyclic. Cycling means like it will cross your positive to your baseline to a negative part. That means it is always kind of we call as a reverse cycling. Reverse cycling means like the maximum positive displacement or maximum positive acceleration would be more or less similar to the maximum negative displacement or acceleration. So that's why, like the wind, the loading design provisions are not applicable to the earthquake loading design. So the third point is like probably like the wind loads are actually acts on the structure directly, mostly on the superstructure in form of the pressure, whereas the earthquake loading actually is generated from the ground and transmitted through the members to from the ground to the top floor level. So that means you need to convert the loading or the demand generated at the base level to different levels of your structure, like maybe first floor, 10th floor, 20th floor, depending on the height of the structure. And then what is the response of the structure you expect? You design the structure mostly limited by the yield point. Your most of the design is in linearly elastic point actually. Whereas during the earthquake, you expect that it should damage. So damage in the sense that means you are expecting that your structure should behave in this range, whereas your design is actually mostly limited in this. But so that we'll discuss in the second lecture today, like what is performance based design. But having said that, so what is your intention should be, since during the earthquake you are expecting that your structure would actually may reach this point or this point or this point. So that means you should have a sufficient ductility in the structure, you should have sufficient strength in the structure or the member or the material during the earthquake loading. So there are some uncertainties in the earthquake, and there are similar uncertainties in the design also. If I look at the earthquake, which is essentially the input loading, so you can't predict, we don't know the magnitude and the location when there will be an earthquake. The nature and type of the fault is also to some extent is uncertain. Again, the variation in the soil condition, local geology. So there are a lot of uncertainties in the ground motion itself. At the same time, you have some kind of uncertainties in the estimation of natural period, damping, inelastic behavior, soil structure interaction like this. So the way we actually take it or design a structure for earthquake loading is we don't consider the minor earthquake, and we also at the same time we can't neglect the severe earthquakes. So mostly the design is based on the not exactly moderate earthquake, around that level, which we call as the design basis earthquake. And the severe earthquake we actually define as called as the maximum considered earthquake. So most of the design is based on the DV level earthquake, and the design you do based on the DV level earthquake must be, must give you the satisfactory performance in case there is the same structure is subjected to severe earthquake. So what you do here, so you know that like there will be the earthquake at the ground, so in form of the, let's say, acceleration, and that acceleration will be transferred to your floor level, where you have a slab and beam where the mass is essentially, if you take a cross section like or section here, you section here or section here, you'll see that the at this level the mass is concentrated, or if you estimate the mass at this level, it will be significantly higher than the mass here and mass here and mass here. Why I'm talking about the mass? Because the earthquakes gives you the excitation in terms of the acceleration. So if I multiply with the mass, that gives you the force. Now, ideally, there is earthquake force at any point, over the height of the structure. But if you try to calculate the magnitude of the magnitude of force at this level is significantly higher than the magnitude of force at this level, at this. So essentially, if you just make some strips and try to find out the mass of the structure, you can find the total force is your mass into acceleration. So in that context, what we do is since the level of force at this level or the magnitude of force at this level is higher than any other points. So in the most of the times, like what we say that like my earthquake force is actually being applied at the beam or the floor level rather than considering this the forces continuously throughout the height of the structure. Now, what the objective, like that means your force is applied at this level. However, these two supporting elements, maybe in masonry wall for the masonry structure or the columns for the frame structure, they should actually transmit this force from this level to this level safely without any significant damage or collapse of these supporting elements. Now, coming to the earthquake motions, actually, you know that like earthquake is random, so it not necessarily it will act in a particular direction to your plan of the building. Like maybe X direction is the plan. If you take the building plan, this is X, this is Y. Not necessarily your earthquake will actually apply in the Y direction or X direction. At the same time, your actual earthquake ground motion may be inclined to your horizontal plane. That means there will be a component of the vertical component which will apply to this to a particular structure. So at any point you have X and Y and Z. So these are the not exactly the earthquake applying. So this is essentially like you will get the one directional wave, and then depending on the plan of the structure of your interest, you resolve that in X direction, Y direction, and the Z direction. So that means any ground motion, we can uh, resolve in three directions. So two horizontal and one vertical. Now the question is why two horizontal, like along the orthogonal direction? Because I'll come to that little later. Essentially, to just to facilitate the design, but not that doesn't mean that earthquake will only be applied or act in this direction or the y direction or the vertical direction. So essentially any ground motion we can actually have the three components resolved in three components. Essentially the recorded device which you get earthquake data, time history, you orient these the device recording system so that you get three components, that is longitudinal, vertical, and transverse. And same three directions probably like we can resolve in our design case. Now in the horizontal and transverse, essentially the horizontal components at longitudinal and transverse, they are the one which is more damaging in nature because they apply kind of in the lateral direction. The vertical component which acts probably like if it is acting upward, so it is acting against the gravity. That means your structure is subjected to lesser vertical load. But when it is actually pulling down, so that means the gravity load is actually increased in presence of the vertical component. So for many structures, the vertical component is equally important than as compared to the horizontal component. But for the buildings, mostly the horizontal components are the critical one. And so when all these three components of the earthquake is applied to a structure, so your structure should, and depending on the force level and the direction of the force applied, your structure should have sufficient load path to transmit that force from the floor to the ground level. Now, what is the basic concept? Probably this is one of the fundamental concepts of the seismic design. Now, how the earthquake design has been derived. So let's look at this structure. It's a two-story structure, and you apply some force. So what we discussed, like actually, like there will be some kind of ground motions which will be transmitted to, or acceleration which will transmit it to the floors, and floor into floor mass into acceleration, you get the force. Now, if I add this force here, I'll add this force here, and if you have multi-story structure, keep adding those forces, you will get some total force, and that we called as the design base shear. Now, for the time being, you forget about like what is the design base shear. Let's think of like I have a structure. You apply a total force here, which is equals to the design force, and try to uh, measure the displacement at the roof level. You apply the force at the roof level and measure the displacement at the same level. Now, if I have a structure, probably like depending on the size of the beams and columns, what we'll get is in a practice, you apply 10 kilonewton, you will get, let's say, 5 mm. You apply 20 kilonewton, you probably get 10 mm, 40 kilonewton, 20 mm. So that means you have a linear relationship up to some extent, and after that you will get a non-linear response, because it all depends on how your beams and columns are actually designed. You think of a structure which has the columns and the beams are very, very thick. For example, Taj Mahal. So what happens? Like those kind of structures are probably give you a very high, linearity response. That means you keep applying the force at the top, your displacement to the force will be always directly proportional. So that means if I take a structure which is linearly elastic, that means like you apply any force, it would not damage, it will not go to the inelastic, or there will be no yielding. So probably that would be something like the force deformation curve will be something like this. So that means I can say that if my structure is perfectly linear elastic, the force deformation response, that is, you apply the force, get the displacement. So this is the force axis, this is the displacement axis, this will be always linear. Now what happens that, like in the practice, so for this linear type of structure, if there will be any earthquake, probably there will be no damage. But to get this response, linear force displacement response, your beam and column size should be extensively thicker. Like it's very, if you ever visited the Taj Mahal, you can try to find out or figure out what is the thickness of the wall in terms of the meters. Now, there are two cases. One is like building a structure which will behave linearly elastic. That means there will be absolutely no damage, there will be no yielding, there will be no cracking, would actually demand a very thicker wall or very big column sizes or beam sizes. Now that is number one. So there is a cost implications. At the same time, you are not sure that during the life period of this structure, so that every structure has some design life. During that design life, whether the structure will be ever subjected to an earthquake or so-called a damaging earthquake. So there is no guarantee that the same structure will be subjected to a earthquake which is damaging in nature. And at the same time, if I am trying to build a structure which is probably inelastic or behave elastically, so it would actually give I have to spend a lot of money, and which is probably practically impossible for building all kinds of structure, except is a unique structure or heritage structure. Number two is the kind of construction we are doing right now. For example, reinforced concrete structure or the steel structures. We know that, for example, like steel reinforcement bars or structural steel I section or the channel section or any kind of sections, rolled sections are available there. If you take their a coupon and do the material testing, you will find that the stress and behavior will be something will be elastic, then you have yield, then you have ultimate, then you have collapse. That means the linear part is very, very small as compared to the non-linear part. Non-linear means after the yielding point. For example, like if you use the mild steel, your fracture strain is around 20-22%. That means the point where it will fracture. And compared to, and if you try to find out the strain corresponding to the yield, that would be around 0.125%. So 25% is the failure, and the inelasticity or damage is starting at around, let's say, 0.1%. So we have a ductility of 25 by zero point 0.1 is more than 200 ductility in the material itself. So that means if I exceed that yield point, it doesn't mean that my structure is going to fail, because the failure is there once you reach the ultimate point and collapse point. So you have a material ductility inherently implemented or is there in the material. The second, the same material, if I'm going to use in a beam and I test that beam, what you will find that, so when I say that your beam, you design the beam, your design is based on the yield point. But due to that material strain hardening, your beam would take the higher load than it was designed, because your design is always limited by yield point, but your material has the strain hardening and then the ultimate point before it goes for the collapse. So you have the inherently overstrength due to the strain hardening, and at the same time a material of 250 grade steel, when you actually test in the lab, you will always get 260, 270 as the yield point actual. So you have overstrength in the material, you have overstrength due to strain hardening, and your design is not based on the ultimate, it is based on the yield. Now the same, so you have the overstrength in the material, you have the overstrength in the beam itself, because if you design a beam for 250 kilonewton meter flexible capacity, probably you will get 350 kilonewton. And when we combine multiple members, beams and columns, you get additional strength. For example, like you have beam capacity, you have the column capacity. It is not only the beam capacity and column capacity. If you remember the structural analysis, you try to do that. If I ask you what is the collapse load, you try to find out what is the plastering hinges, like sway mechanism or beam mechanism or frame mechanism. That means you only take care of the capacity of the beams and columns. Again, in that capacity, like you take MP equals to Fy into Zp, but actually your steel can take Fu. So that overstrength part is already there. At the same time, you have the joints, and these are the mostly the rigid joints. And if you have a rigid joint, the rigidity of the joints will also give you the higher strength than you expect. So what I'm actually making here, so it's called the redundancy. So in a structure, it's composed of members fabricated used from the materials. What the parameters involved in a structure are, you have the ductility. Of course, the material ductility is different from your member ductility, is different from your structure ductility, but there is some ductility. The second, you have some redundancy. Redundancy means you have the strength or the resistance of the structure coming from the joints. And third, you have the overstrength. Overstrength means you always design based on some specified values, but actual strength will be higher, and your design is most limited by the yield, but you have the ultimate strength also. So the kind of materials we are using, kind of structure we are building, so there are three things inherently there which we don't take in our design considerations. So the first, building a structure to behave completely elastic will be very, very expensive. Second, there is no guarantee that the structure I am designing will be subjected to a damaging earthquake during its lifetime. Third, a structure has some additional properties which I am not taking into my design. So considering these three different values or three different parameters, the earthquake design concept has been evolved. The concept is simply remains same. When you say that, like, the seismic design concept is only determining what is the earthquake load I have to take in my analysis and what kind of detailing I have to do so that my structure will behave well in or during the earthquake. So the concept is like, you first assume that, let's say you are going to design a 10-story structure, reinforced concrete building. Let's see that if the same 10-story building I am going to build, and that building will not get damaged for any kind of earthquake, that means the structure should be a linearly elastic structure. Now, if it is a linearly elastic structure, what is the force I have to apply? It is simple: mass into acceleration. So if I can estimate the total mass of the structure, or total seismic mass or total seismic weight of the structure, and multiply some kind of acceleration which I'm getting from the earthquake. So that is the force I have to apply. That is the total force I have to apply or I have to consider. So that, and I have to design for that force. So that force we call as the maximum elastic force is simple seismic mass into the acceleration. I'll come to that, how to calculate that acceleration. Now, if you take this maximum elastic force for your design, so one would expect that my structure will behave linearly elastic. But this force level will be very, very high. And considering these three parameters, so what we can do is, we know that my material or my structure or my member are ductile to some extent, whether it is steel or concrete. You will mostly, the ductility comes from the steel, but to some extent your concrete also gives you some kind of ductility, although it's very limited. Now, kind of structure I having, so mostly it's, let's say, steel structure, and I have a ductility in the steel. So what is the concept that I can correlate? Now let's say for a 8 magnitude earthquake, I have some acceleration. I get that A multiplied by the seismic mass, I get some force. Let that force is 100-ton force, which is this force. So if I take that 100-ton force and do the analysis, I'll find out the member sizes. And then if I do an analysis, I will get a linearly elastic structure. Now, if I drop a line here, if I drop a line here, so this is 100-ton for which I have designed the load or designed the structure. And if I apply 10, you will get some displacement. 20, I get some displacement. So let's say for 100-ton, which corresponding to, let's say, some kind of earthquake level. So this is the area which we call as the strain energy. One can calculate, like, if I know this displacement from the analysis, let's say 10 mm, I can take the half 100 into 10. This is the energy which the elastic structure will absorb when there is an earthquake corresponding to this force. Now, considering the uncertainties and all these things, what I said that, because I can't change my earthquake, but I can change my design, keeping this energy constant, because this is the energy which will come to your structure. And if I say that this is the energy I have to either absorb in a structure or dissipate, there are two different things. Absorb means you apply this and it will just absorb without dissipating. And dissipate means there is something by, like the cracking or yielding. So if I try to keep this energy or this area intact, and instead of a linear line, I'm going to draw something a bilinear line. And let's say up to this point, this area, I'll get some energy because this is force and displacement. This is also energy. If I equate this area to this area and keep, so what you are looking at here is you are reducing your force level from 100 to, let's say, I say 70. At the same time, you are increasing your displacement from 10 to, let's say, 20. If one can equate and find out. And since the reduction, and why I'm actually relying on this, so the first thing, when you reduce this force from here to here and increase the 10 to 20 displacement here to here, now the moment you say this is a bilinear, that means there will be some yield point, and that yield point would mean that your structure will be damaged, not collapse. Because your stress strain diagram, you remember there is a yield, there is a strain hardening, there is a ultimate. I'm just talking about the yield point. So you reduce that, so that means this 100 kilonewton you reduce down to 70 kilonewton just because of ductility in the structure. So that means you know that why I will keep myself 10 when I can go up with the material strain up to, let's say, 10 or 12%. So I can always increase the displacement. This is only due to ductility in the structure. The second point, when there are multiple structures, the elements are connected, I said that there will be some redundant, like the joint behavior, there is some connection here. These kind of points, they give you the redundancy. And that means this 70 kilonewton, I can further reduce down to, let's say, 70 ton, I can further reduce down to 50 ton, knowing that there will be additional strength I will get from the redundancy. And then from this, I can further reduce down, knowing that the yield strength I am actually taking in my design is 250, but actually I will get 260. The second, I have the strain hardening. I have a ratio. I know the ratio of the ultimate to the yield of around 25%. So if I include all these things, probably my 100 kilonewton force, which I'm designing that, assuming the structure to be elastic, I can probably reach to a level of, let's say, 10 or maybe 20 ton force level. So what you are actually designing here, this is the design force is 20. And when you actually do this, remember that you are bilinear means you don't expect your structure will be not damaged. The moment you deviate from this line, there will be damage, but there will be no collapse. Okay, so what essentially it actually gives you, that due to ductility, you actually get the yield load. Due to redundancy, you get what is the point where the first yield will occur. And when you include the overstrength, then probably that would give you the design force. So in your structural design, earthquake or seismic design, there are your design seismic force involved inherently 3 parameters into account. One is ductility, one is redundancy, one is overstrength. So the ductility is defined by, like, there is a strain ductility or displacement ductility. As I said, you have a material ductility, which is the maximum strain to the yield strain. There is a member ductility, which is probably you can say the maximum curvature or maximum rotation to the yield curvature or yield rotation. Then you have a structural ductility, where I can say that the maximum displacement to the yield displacement of the structure. Now, if this is delta, you say that the delta max, delta y is the ductility of structure I'm talking about here. What is overstrength? Overstrength is nothing but you have yield strength divided by the design strength. Okay. Now, the reduction in the force which you get from the ductility, that is called as the ductility reduction factor, and we call this factor as, let's say, R mu. That is 100 by 70 for this example. That gives you the ductility reduction factor. And now if I know the overstrength factor, that overstrength actually sometimes this, it is very difficult to estimate this redundancy and overstrength, independently. But if I club together as the overstrength and we say this is omega. So from this point to this point is a combination of your ductility reduction factor and the overstrength factor. And these two, from here to here, what we called is the overall response reduction factor. That means if my 100 ton is the elastic force, my design force is 20 ton. So my response reduction factor R is I'm getting 5. Okay, so sorry. So this is the basis where the seismic design has been evolved. It takes care of the uncertainties to some extent. It takes care of the realistic material behavior, structural behavior, and the material overstrength. So considering this, your IS 1893 actually gives you the two methods. One is the static method, one is the dynamic method to design a structure. And static method is mostly known as the equivalent static method, ESM. Some of the codes, if you go to the American code, they call the equivalent lateral force method, ELF, but the concept remains same. The concept is you calculate the elastic force, that is M into A. M I can replace by W by G into A, and you calculate the design force by dividing R. This is called the equivalent static force method because you are trying to find out the equivalent force by simply multiplying Mi into Ai, that is mass at ith floor to the acceleration at ith floor. Okay. This equivalent static method is only applicable to the regular building of 15-meter height and in seismic zone 2, or a regular structure whose time period is less than 0.4 seconds. Any irregular structure or any structure more than 50 meters located in seismic zone 3, 2 or 3, mostly it has to be analyzed or designed based on dynamic method. The dynamic method actually it comes from structural dynamics. It's for the response spectrum method, time history method, or modal time history method. Currently, like mostly this method has not been used in detail, but this is the two methods which our code recommends to go for any structures. For simple structures, one can use the equivalent starting method. Otherwise, one has to do the linear dynamic analysis to all the structures except the structure falling in two categories. So equivalent static force method is essentially you calculate the maximum force and reduce by R. That gives you the design force. Okay, and the design force we call as, this is the force, the total force is called as the design force level. You remember that is nothing but your something F1, F2, F3. But what we do is we first calculate that what is the force, which is design force, is this a design base shear. So remember this design base shear is nothing but the lateral strength of this frame. What is the maximum force which can be applied at this level so that the structure can resist that load? Okay, so I have already mentioned there how it is calculated. Is the force you are calculating. So the force is M into A. and the only thing is M, your code actually gives you in terms of the M is, weight, that is your seismic weight of the structure, and it is multiplied by, yes, some kind of acceleration, but this is nothing but the acceleration. This is acceleration by G, because when you replace M by W, so essentially you have acceleration by G, and so A by G is nothing but your design seismic design horizontal acceleration coefficient. So it's just a coefficient because you have a W, but essentially it is mass into acceleration. Okay. Now, how you calculate this? The W is your seismic weight left here. Now, for the time being, you forget about this I. So that means it would be something A. So what I can write down here is W by G into A. That is mass into acceleration. That becomes your force, right? Now your acceleration, how to get this, the design acceleration coefficient, or the design acceleration. So this design acceleration, which should be in the form of meter per second square or something, it comes from your seismic zone, soil conditions. Okay, so your code actually gives you different codes of different concept, but essentially they gives you this value, that is A. Your code, your IS 1893, it gives you some A equals to Z by 2 into SA. That is your, not SA by G, this is only SA is your A, right? And this I, this is nothing to do with your acceleration, it is just the importance, that whether you have residential structure, you have a essential facility structure, a critical structure. So this, you just simply multiply this acceleration by 50% or by 25% there, and so this acceleration divided by your response reduction factor. So that is simple as that, how to calculate the design base shear. I'll come to that, what are the meaning of this and how our code actually take care of this. So there are two things. Z by 2, you can think of like something Z factor, SA, R, and I. So current seismic map is like this. That is probably you are looking for the last time. This is seismic zone map. The next year you will, toward the end of the next year, you will get a new seismic map, which probably will be little different from, which is more rigorous and more realistic map, which will, and then there will be some difference in the on these factors. Rather than giving the zone factors, you might get some acceleration factors also there. So that is in the process by the code committee. Anyway, so currently as of today, so there are 4 seismic zone. So the fifth zone is your highest one, and it actually defines some kind of value, 0.36 to 0.1. Now, if anybody actually aware of some kind of recorded ground motion, there is the El Centro ground motion. And probably the El Centro ground motion is the basis of many of the codes. And El Centro earthquake, and during that earthquake, the maximum PGA was around 0.34 G. And that was the basis, probably like this 0.36 was being fixed. So it's a kind of a acceleration. The zone factor gives you kind of a, is nothing but a kind of a your acceleration. So if I say that is not a factor, I can say for my zone 5, the maximum considered earthquake, MC, is 0.36 G. Now, since everything we called for the design, that is based on design basis earthquake, what we do is we divide this, probably I missed this slide. Okay, so so what we do is this 0.36 is for the maximum considered earthquake, and layman's point of view, for the severe earthquake, for the design, mostly the relation between the MC to dV is 1.5. So our code conservatively take care 2. So that's why this becomes Z by 2. Otherwise, it should have been like, if again the 1 point, so it should have been dV value should have been Z by 1.5. But this Z.36 actually not clearly or truly represent the MC level, little higher. So our code actually conservatively take that 2 here. So essentially this is some kind of acceleration comes from your zone, and then at the same zone you may have the different site conditions, and you would have different structures that actually comes in your SA by G curve that is called the design response spectrum. Like if you have a structure which is very, very flexible, your SA comes at this level, like let's for the 2 seconds or something. If I have a very stiff structure, so this factor is being multiplied with your Z by 2, gives you the actual, if I say that what is the acceleration, so it's the Z by 2 into SA. So that is your design acceleration. And if you remove the 2, that becomes the design MC level acceleration for which you design your structure. And remember, this acceleration comes, SA is a function of your time period of the structure, because the more flexible structure, you have the lesser spectral acceleration, you have a rigid structure, you have the higher spectral acceleration. So one is coming from your zone factor, comes from your locality, your soil local condition, and at the same time you have the different soil. So for example, hard rock or the medium soil or soft soil. So there are the 3 different curves for the soil to consider soil conditions. Then you have the importance factor. Importance factor, as you know, for the critical structures, the lifeline structure 1.5, 1.2 is for the business or community structures, and 1 is for the rest of the structures. It's just amplifying this A by either 50%, 20%, or probably not amplifying for the residential structures. Now, when you design the structure, the natural period, I say that you have to find out the SA by G. The question is, I am designing a structure, how to determine the natural period? So the codes gives you the approximate conservative fundamental period. When you try to find out the natural period of the structure, actual natural period will be always greater than this. But this is conservative in the sense, like if your actual time period is 1.5, probably like the code estimate time period will give you 0.8 or 1, because the code inherently assume that you will take a higher design force in your design consideration. So there is no way your actual time period will be matched with your this time period. This is always conservative, because you probably, you can say the least fundamental period for a particular structure, if you can say so. So it gives you for the different kind of structures, like for the moment resisting frames, that is only for the beams and columns with the rigid connections. It gives you for the reinforced concrete building. It gives for the composite structure, for the steel. It's just a function of your height, and you know that actual time period depends on the mass of the structure and stiffness of the structure. Mass and stiffness of the structure, they actually are a function of the area of the slab and the column dimensions. But this equations TA, which gets the approximate time period, is very, very conservative. It only gives you an idea that what would be the time period for which I have to calculate the SAYG. Similarly, for your RC structural wall, there is a function AW, which is the area of your total effective area of the wall. It's a function of your aspect ratio. And then you can find out, like if you have a RC structural wall in the building, then you can use this formula. And for all other buildings where you have a masonry infill and probably any other buildings which is not coming under the MRA for the structural wall system, one can use this formula to just find out the SA by G for the design force estimation. Now the question here is how to find out the H in different kind of structure. Like your structure may be like something like this, which is your ground level is here, but your structure is a little below the ground level. Or maybe like your structure may be like you have a some kind of basement here, or you have the structure which is on the hilly slope. So the H is in this kind of structure, the H you calculate or use in this formula for this structure is starting from base to the top. For this kind of structure where these are the stiffer one, you can see the difference between this and this is this part is little stiffer and this part is actually the connected to your ground. So the H will be like mostly the clear H. And this kind of stepped structures, one has to effectively calculate the area and HI by AI the way you calculate your central or CG of the section. And for the structure supported on the hilly ground, so the H is something measured in this way. That is the height of the structure, not this structure. Okay, so why you have a smaller H? Smaller H will give you the smaller time period. Smaller time period will give you the higher SA by G. Higher SA by G give you the higher design force. Because when you do the design, you design for the maximum value. Okay. Now coming to the response reduction factor, which we discussed, that is a function of your ductility, overstrength, and the redundancy. So your code this time 2016 version gives you for very detailed provisions for different kind of structures. So it includes the moment resisting frame. Moment resisting frame means you have beams and columns. Braced frame means you have beams, columns, and the braces in the diagonal pattern. And then you have a structural wall. It might be concrete wall or the masonry wall also. And in sometimes you have a dual system. Dual system means like a combination of moment frame and the wall system. And you may have a flat slab structural wall system. That means you have a structural wall only and then flat slab. If you can see that the R value varies from 3 to 5 most of the cases. So 3 being for the ordinary one and 5 being for the special one. Now the ordinary and special is essentially dependent on how much you are extending this point to this point. That means what is your reliability in the ductility. Now remember this ductility I am talking about the structural ductility, not the member ductility. Okay. So the structural ductility or member ductility are different. So to get the structural ductility, you have to do some kind of detailing in the members. Okay, and when you follow a detailing to achieve some kind of a higher rotation or higher ductility, that is called as the special ductility or the ductile detailing, or so special detailing, or we call in the seismic term we call as the special detailing. And the special detailing or ductile detailing, when you implement that in a structure, that becomes your spatial structure. So is either spatial moment resisting frame or the spatial braced frame. That means you do something related to structural ductility or the structural so the detailing of the joints or detailing of the members, so that you get higher deformation or the higher ductility. Now, just to give an idea, like a moment resisting frame, you have beams and columns with some kind of rigid, all the joints are rigid joints. Shear wall, you can see there is a wall, it is there some openings on the wall, so this is called the wall system. Then the brace frame, you can see this X brace, or the brace may be like this way. This is another brace where the BRB, so this is kind of brace. And sometimes I may have one braced frame and one moment frame in the same frame. Okay, and that is called as my dual structure. Or it might be a RC structural wall with moment resisting frame in the same frame. That's called as the dual system. And for the dual system, it gives you 3 to 5, again depending on the whether it's a special moment resisting frame or ordinary moment resisting frame. So maximum R value is 5, and the minimum one is 1.5, which is for unreinforced masonry wall. Ordinary moment resisting frame is 3. Okay, and so it's essentially mostly 3 or 5 for ordinary and special frame. And then you have to estimate the seismic weight. Seismic weight is not only a function of a dead load, it is also a function of live load. But during the earthquake, not necessarily all the design live loads are applied. So what you do is you read, the code recommends that when you calculate the W is not DL plus LL, but it's a DL plus alpha into LL, which is a proportion net live load you take. So what you say that, like, if your imposed flow load is more than 3 kilopascal, so you take 0.5, and when it is less than 3, you take 0.25 as the alpha to calculate the W. When you calculate this SA by G, Z by Z I R, you calculate, you get a AH value, that is called the seismic design coefficient. You have to ensure that this value should not be less than the value mentioned here. Even if, let's say, for zone 2, you are getting AH as 0.5, okay, but you have to minimum take 0.7, and similarly 0.7% actually, so that is 0.005, so you have to take 0.007, and similarly for zone 5 you have to take 0.024 as the minimum design earthquake lateral force in your structure. Okay, so that is percentage of the force or the mass, you can say. Okay, so first you calculate the AH and you compare that AH with these minimum values, and if his AH value is higher than this, then retain that, otherwise you take this minimum one. Now you calculate the force at the base level, but you have a multi-story structure, so your code gives you some parabolic equations to distribute this. What should be the Q1, Q2, Q3, Q4 at all the structures. Remember, when you add Q1, Q2, Q3, Q4, that must be equals to your VB. Okay, so why you would need this? Because you have to analyze the structure to find out the bending moment, shear force, axial force, so that you can estimate what would be your percentage of reinforcement, what will your dimensions. So in addition to the dead load and live load, you have to also apply the earthquake load and the wind load. And so for that, you have to calculate the QI, that is, you have to apply what is the force you have to apply on the structure. And these are the some kind of applications, combinations you have to take depending on different types of codes. But since you have a structure which is a 3-dimensional structure, and you know that the earthquakes can, mostly it is not necessarily aligned with one of the direction of the plan dimension. So the code says that you take 100% load in one direction, if I say in X direction, and you take 30% load in the Y direction and 30% load in the Z direction, and similarly take one more combination for Y and take one more combination for Z. For example, like, you have the load combinations, you have you have 3 cases. One is 1.2 DL plus LL plus earthquake load. You have 1.5 DL plus earthquake load, or you have 0.5 DL plus 1.5 earthquake load. So all these applications or all these combinations, you have to take all these kind of possible combinations. That means with plus or minus combination. That means in one direction we apply in the left side, other direction we apply the right side. So what essentially says that you have to take care of not only the one direction force, you have to take the interaction between the force in one direction with the force in other direction. So this is the equivalent static force method. In the response spectrum method is dynamic analysis method. When you have to do the dynamic analysis, there is a change in the spectrum to be used in the response spectrum method. Remember, it starts from 1 and it's the linear curve, right? So if I show that, like, but in this is again the same spectra, but the linear part is not there when you do for the equivalent starting method. This is a change from the previous version of your code. Okay, so it's at 0 it is 2.5 if you are going to follow the equivalent starting method, but if you are going to follow the response spectrum method, it starts from 1 to 1, and 2.5 it is something at this point. Okay, so there is a little bit of change the design space response spectrum to be taken in the response spectrum method. So this one either you take from the code, or for the important structure you need to derive this response vector. For example, you are going to build a dam, so you have to see what are the earthquake records are there, and then you have to establish that. And so in this method, what you do is you do the undamped free vibration analysis of the structure. So you model the structure in some of the software, or maybe you can have your own code. You find out the natural frequency and the mode shapes of the structure. Now you have 20-story structures, there may be 20 modes, but how many modes you have to take for your analysis? It depends that you have to first find out the sum of the modal masses, which can be calculated from this formula. And so if each mode has some modal mass. Let's say mode 1 has 78%, mode 2 has 12%, maybe mode 3 has 3%, mode 4 has 0.8%. It is not necessary to take all the modes. It's good enough if you can take only those modes, or 4, for example, like for first 3 mode or first 4 modes. If some of the modal masses gives you at least 90% of the size free mass. So if only 3 modes of a 20-story structure is giving you the 90% size free mass, only take the 3 modes. So for the calculation, that means for each mode you calculate the peak displacement, you calculate the peak time history, you calculate the peak acceleration, you calculate the peak base shear, lateral force, you calculate all these parameters. And then since you have more than one, so you have 3, or let's say 3 or 4 or 5 modes which are actually contributing 90% of the modal mass. So you have to actually combine those. That is called the modal combination rules. In the modal combination rules, it's essentially based on either the CQC method, which is the central quadratic coefficient method, or it's the sum of square root of sum of the squares. So square root of sum of the squares, that means if you, let's say, first at the roof displacement is one of the parameter I'm talking about. In the first mode you get 10 mm, in second mode you get -5, in third mode you get 2 mm. So what is the value I have to take for my analysis and design? So in that case, what you have to take the 10 square plus -5 square plus 2 square, if only the 3 modes are contributing to 90%, and then take their square root. That would give you the final roof displacement. So you can do for the same the force at any floor level, lateral force at any force level, floor level. You can calculate the acceleration at any floor level. This is how it is calculated. And similarly, like in the CQC method also, this is the ith mode, this is the jth mode, and then you have the interaction. And when the two modes are actually placed together, that means, like, say, one fundamental mode is 1.01 and second is 1.02. So in that case, you can only take the absolute values of the response quantities. But when you calculate these response quantities, like for example, let's say you follow this method and you find out the lateral force at one of the floor, or the design force at one of the floor, at the base. If the design base shear calculated from the response spectrum, so that value must be checked with the equivalent starting force method. So in no case the value of base shear you get from this method, response vector method, should be less than the design base shear you calculate from the equivalent static force method. That is your W by M, VV by your Z by 2 SI by G, I by R into W. So you anyhow you have to calculate that base shear, and in case if the response spectrum value is higher than this value, using the equivalent force method, then you consider that as the final and go for the analysis and design. In case the VV or the design base shear for the response spectrum method is lesser than this value, then all the quantities must be multiplied by a factor called the base shear, calculated from the equivalent static force divided by the response for spectrum method. For example, here you get 100 and here you get 90, so which is less than this. So what you have to do is all the quantities you calculate here must be multiplied by 100 by 90, and that would be your final. The second method, in the time history method, what you do is you take a series of ground motions and you do a linear dynamic analysis of the structure, and these ground motions, the time histories must be probably compatible with your design acceleration spectrum. That means for time history analysis, whatever the acceleration you or time you say, that you have to see that they are actually spectrum compatible. That means actual response spectrum like you get from the time history should not be like this. So that there has to be some compatibility between your design response spectrum and the actual response spectrum which you get from the recorded ground motion, and take that, apply that, and then you perform the analysis in combination with the gravity load and find out the total displacement and acceleration and design the structure. Either you follow the equivalent static force method or response spectrum method or time history method, you need to check the story drift, and the current codes say that, remember, these are all linear dynamic analysis. You are not following any non-linearity. So in the analysis, the linear analysis, you have to check that at any flow, the displacement of the story drift we called as, right? It should not exceed 0.4% of the story height. If the story height is 3, so the relative displacement of the top and bottom floor level should not exceed 3 meters, should not exceed actually, kind of a 1.2 meter, right? 3000 into 0.4 is 0.4% under that size. And here, when you calculate the displacement, you should not use any load factor, that is 1.2 or 1.5. All load factor should be unit. The same model, you have to just apply the load and check that your story drift should not exceed 0.4%. If that is the case, then your structure is safe and your design is okay. In addition to this reinforced concrete frame, your IS 1893 also gives you the guideline for the frame with the infill wall. That means it's one of the very most common structure. You have RC frame with the infill wall. Infill walls, masonry infill wall particularly, are very, very stiff and very, very strong in plane. In plane means if you apply the load in this direction. Out of plane, that means you apply the load in this direction, definitely they are weak. So when you apply the earthquake and there is a infill wall here, you have to take the in-plane stiffness and strength into account. So in absence of the data, the code gives you that how to calculate the Young's modulus of this infill wall and how to calculate the strength, compressive strength of the masonry infill. Okay, it's based on the Indian conditions. And how to model that? You don't have to model the entire infill panel. So if you are modeling beams and columns, so the infill panels need to be modeled as a one brace, which is called the strut. For the dynamic analysis, cycling nature, you have to apply the two braces. So one diagonal, these both are same actually. So one diagonal represent this one. Okay, and this diagonal, how to find out this, the width of this diagonal or something, it gives you some kind of guideline that this is the width, that is W. Okay, and so this is a function of your EM and moment of inertia of the beam and columns, and of course the angle theta to which your strut is there. So essentially it's you have a brace. So for a brace, what you need need to define your cross section. So it the thickness is your thickness of the infill panel. The width will be determined from this formula, and then material properties, the Young's modulus and the compressive strength or the Poisson's ratio you have to define. So in your STAD model, simple thing is you have to just model as a some brace member which is called as the infill diagonal strut. Now, once we do this analysis and design, what you do here is you calculate the reinforcement. You find out the sections based on the PM interaction and shear, right? But for detailing, ductility, because you remember that you are always stretching the displacement from 10 to 20 or 40, right? So that is, you have to also ensure that the two things, during the earthquake, the structure should not collapse. Or I should ensure that the repair cost, retrofitting cost should be minimum. So what to achieve this? So you have to design or in fact detail the structure in such a manner that you can prevent the collapse. At the same time, you spend minimum money to repair and retrofit. So for example, how to decide that I have so many members, like components, columns, beams, slabs, foundation. So which one is the critical? So the if I can find out the critical elements, I have to design that critical element should not be damaged excessively, so that otherwise either it will lead to a collapse or the cost of retrofitting will be repair will be significant. So keeping that in mind, so there is a hierarchy is followed in earthquake design, and it's mostly related to the failure of the structure. The second one is, so that means hierarchy means which element I can afford to get it damaged more, which element I can afford to not allow or probably damage to minimum possible extent. That is called the hierarchy. The second is what kind of damage I should actually looking for. You know that if you take a beam, concrete beam, and apply the transverse load, the same beam may fail in shear, and the same beam may fail in flexion. So should I go for the shear failure or should I go for the flexible failure of that beam? Ultimately, if that beam need to fail. So it is not only the critical elements. Also, I have to also see that if I am allowing a member to be damaged, what kind of damage it should go through. So the second question is very, very simple. Because your shear failure is gradual, sudden, it actually lead to an uncontrolled failure or collapse of the structure. The goal is to always prevent the shear failure. Ensure that your failure is due to flexion. So when you do something, you design or detail your structure to get a ductile mode of failure. The detailing is called as the ductile detailing. Okay, and what is that ductile detailing? Means you prevent the structure, the member, from undergoing the shear failure. So ductile detailing is not the flexural detailing. The ductile detailing means you are looking for a ductile behavior, flexural behavior. but actual work you do to prevent the shear failure. That means your design, your ductile detailing is nothing but your shear detailing. Okay, so that I will come to here. So the first thing is, second part is actually clear that I need a ductile failure. Thus, if I come to the first question, probably like if you see that like if I in a structure you have beams, columns, slabs, all these things. If there is some liquefaction or there is a foundation failure, how strong your beams and columns are, your structure will collapse. So probably the soil or the foundation are the one of the critical element in the structural design. So you have to ensure that if anything occurs or if any failure there is chance to occur in the foundation, that should be the last stage, not the first stage. So that means, in other words, if I would actually I will given a chance to damage an element, probably I would first are happy to damage a slab, because a slab is limited to only one room or probably the two adjacent above and below rooms. So all other rooms will not be affected. It's just repair I will do for that slab. But most of the cases, slab damage is not considered as so some kind of serious. The second one, actually, like if I'm looking for the plastic hinges, so the probably I would prefer to damage my beam first rather than the columns. Why? Because if your beam, one of the beam fail, again only two stories, beam, the story below the beam, story above the beam will probably subjected to some kind of disturbances or construction or rehabilitations. But entire structure remains safe. But if one of the column fails, probably it will attract to partial collapse of the total structure or even total, complete collapse of the total structure. So that we call as the capacity design. Capacity design is you design, you don't follow the concept or the design concept uniformly. You first design the weaker element first, weaker in the sense you want that element to first damage. And then based on the capacity of the weaker element, you design the next stronger element. Then based on the capacity of that stronger element, expected capacity, I'm talking expected means which is probably like the ultimate, you then go for the design of the other element. So the hierarchy is like the first I will design the slab, taking the slab strength, ultimate strength, I'll design the beam, taking the ultimate strength of the beam, I'll design the column, taking the ultimate column of strength, I'll design the foundation and probably the soil. When I say the an ultimate, is probably like you can think of this FU, right, not FY. So what you are doing is, that means when you do the capacity design, you don't rely that how much your columns are subjected to or what is the maximum axial force or maximum bending moment or maximum shear force that column is subject carrying under any combinations. You only look at probably like if you don't model the slab in your stat, you probably like the design forces which you get from the stat are only helpful in designing the beams only. But once you design the beam, then you calculate the beam capacity, not the actual forces which the columns are carrying under any combinations. You take the beam forces, actual capacity of the beam forces, and that capacity you applied at the load for the columns. Okay. So we call that the weak beam and the strong column. That means you can see that your column need to be very, very strong as compared to the weak beams. The gravity load concept always is the other way around. In gravity load design, your columns are stronger than the, sorry, beams are stronger than the columns, but in earthquake design or capacity based design, your columns need to be stronger than the beams. So the weak beam, strong column is the seismic concept, whereas the gravity load concept is the strong beam, weak column. Okay. So let's say this is your hinging, plastic hinging with what you expect in a structure. Okay. So what you do here is like that. This is one of the hierarchy you need. So you can see that these dots represent the damage in the beams. So I want that all the beams, if it is possible, uh, to develop the plastic hinges, but there should not be any damage to my columns. But this plastic hinges in the beams is only possible when the structure is at a deflected position. So to make sure that the plastic hinges formed in the beams, your structure must be something tilted, right? So when the structure is tilted, there is some rotation at the base. Okay, so to ensure that the damage is in the beams, there has to be some this base must allow the rotations, and the rotations are so high that probably like elastic rotation is not possible. So so ideal mechanism like is the plastic hinging the beam and the plastic hinging at the column base. So that means you must allow the column base to go to inelastic region. So that means it is not the retrofitting of only the beams. Also to some extent you have to do the retrofitting of the columns. Remember, the plastic hinging will only form under lateral loading when they will go for the in a lateral deflected shape. If it is in that shape, there won't be any maximum bending moment here, and when there is no maximum bending moment, there will be no yielding. Okay, so that you have already discussed. Okay, so what you do here is you first design the beam, whatever the loads applied. So for example, I from the start I do the all the combinations. I get the P axial force, I get the V, and I get the M. So for the beam, I will not look at this V right now. I'll just take the P and M interaction. Then I will find the what is the AST required for this beam. That is called my flexural detailing. But I am not relying on this shear force. Okay, so this shear force is calculated. So once I define like this is my AST either in tension or compression, so you apply, let's say there are some steels I have to apply, some steel I have to apply. Now probably the requirement is 2.5, you apply 3 here, the requirement is 3.2, you apply the 4 here, and taking these dimensions you find out the moment of resistance of the beam. When you use the moment of resistance of the beam, that is a function of your Fy. But what I need here is, I need the capacity, actual expected capacity. So this Fy need to be multiplied by a ratio called Fu by Fy, right? Because I'm looking at the expected capacity. Because I know my Fu is always greater than Fy. So that M omega, which is not your moment of resistance based on the Fy, but it is a function actual moment capacity or expected moment capacity taking Fu. Now you find out the moment capacity, that is M omega here, M omega here, and taking two bending moments, you find out the shear force. And you, instead of taking this shear force we get from the start, you take this shear force to find out how many stirrups and what would be the spacing of stirrups. So that detailing which you do for the shear is called the ductile detailing. So this AST or dimensions, everything you take from your stat. But once you finalize that what would be the dimension, what would be the number of bars. Then you estimate the actual capacity of the beam, and taking the actual capacity of the beam, you calculate what is the shear force. That is this plus this. If I say this M1 plus M2 by L, that becomes your shear force. And you take this shear force, I can say V prime, and for this V prime, you find out the stirrups. That or do the shear design. Okay. Yeah. So at one end, let's say this is the moment capacity. So this is for concrete. The for shear steel also same thing. M omega is all these things, and then you calculate the V. That is the shear force. Of course, there will be UDL, WL by 2, and this will be your shear force for which you have to design the shear. Okay, and similarly for the joints, you apply this shear, not the actual shear force you are getting from this, because you are taking the expected moment, and then you calculate the shear force here and shear force here, and then you detail the joint. Okay. So for this, for example, for this joint, this is your M, and from this you calculate that, this is for column shear. Column shear, there will be some bending moment here, some bending moment here. So remember, this bending moment is not your 0.87 Fy, AST into your UM. So but it is the expected moment capacity. So your IS 1893 for the reinforced concrete building, take that omega as something 1.4. Okay, and you can see that how for this beam, like this W is again limited design. This is 1.2 DL, DL plus LL, and if it just sways from the right to left or left to right, it gives you that how to calculate the shear force. This 1.4 is essentially the expected shear capacity factor, expected factor, taking the strain hardening into account. MUAS, MUVH, AS means the sagging bending moment. You can see it's a sagging, and this is hogging. So so very often, like the reinforcement at this section and at this section will be different. Okay. So for example, like there will be some steel here, some steel here. Okay. So you will get one sagging bending moment capacity and hogging moment capacity. In this case, this is based on your equation of IS 456, that is 0.87 Fy in D minus 0.42 XU, and that 0.87. So here you have to calculate based on either IS 456 or IS 800, and then whatever the way you would calculate the design capacity. And this 1.4, it actually takes care of the ratio of the yield strength to ultimate strength, and also the factors, partial safety factors taken in the limited design. So taking this, you calculate the shear force here, shear force here for one case. For the same beam, if the loading is from right to left, you also calculate the shear force here, and taking the maximum shear force, you provide the at this section and this section provide the shear stirrups. Okay, these are some guidelines. It say that like what should be the minimum stirrup location. It should not more than 2 inch from or 50 mm from the face. Again, the maximum hoop spacing should not be half of more than the half of the depth of the beam, and then maximum spacing also gives you that some guideline. This is the photo I've taken from the IS 13920. This also gives you that to have proper confinement, proper anchorage, and then without and in order to prevent the failure of the stirrups, what should be your anchorage depth, 6 times D, or at least should be 65 mm. And then if you have a used stirrup or cross tie, how to provide this. So these are some detailings gives you for the beams. These are some detailing for the columns, and if you have more than 300 mm You have to make sure that you provide a cross tie here. Then these are some detailing for your beam column joints. Again, remember that this 1.4 is actually taking based on the capacity design. That means your moment capacity of the columns must be greater than 1.4 times your moment capacity of the beam. And then you apply this column moment capacity and beam moment capacity, and then you find out the shear force and do the detailing. Okay, so this is all about the design practice of the concrete structures mostly, and the concept remains same for the steel structures, and also how to estimate the design process. So I will stop here. I will take some questions from the audience if you have something.
Good morning. Good morning, sir.
Good morning.
So I have one question. In cyclic loading for finite element analysis, how can we assume that magnitude of force is?
Which software you are using?
Sir, it is abacus, sir.
Okay, and what you are modeling?
So I have a model plain concrete beam, sir. This is a 3-point bending, 3-point load system, sir.
And you have to apply cyclic, right?
Yes, sir.
So my suggestion would be like you do a displacement control loading. You know how to do the displacement control loading, right?
Oh, okay.
So or you can do a force control loading, but you have to provide that. Let me see if I can. Can you see the screen?
Yes, sir. Yes.
So the best part is you probably like apply this kind of loading in stage wise.
Yeah, short-footed. Yes, yes.
Okay.
Yeah.
So if you can't do in one stage, you can do the stage loading. Let's say this is for stage one loading. And once it is completed, then the stage two loading should be start from here.
Yeah. Yeah.
Okay. And for displaced, I think you can do for the even for the loading also, but the displacement control loading will give you the post peak behavior. Post peak behavior means you start from here. You start from here and then something like this. So if you do the displacement control loading rather than the force control loading, then you will get the behavior beyond this point. But for the force control loading, probably you get the curve from this point to this point only. Okay,
Okay.
and, but make sure that your non-linearities in the members are actually well defined beyond yield point, like concrete behavior and steel behavior. Okay, so that you will get non-linearity. Yeah,
Okay. Okay, sir.
thank you. Anybody else?
Any questions from the participants? Please ask. Otherwise, you can type in the chat box also. There is one question from a participant, Rimaya. Sir, in the slide which you have shown how to consider H value, what's the difference in the first figure and the second figure? H value.
Yeah, in the first figure, you can see that there is a uniform cross section of the columns. In the second figure, the lower two stories have the stronger columns here. You can think of some kind of very strong walls are here. So that's why like the H calculated from the base here, whereas because this portion is stiffer, so the H is calculated beyond this point.
There is one question, sir. Which document can we refer for capacity based design?
Capacity based design, if you talk about the codes, none of the codes actually give any very detailed guideline, but yes, IS 13920 gives to some extent. When IS 456 also, sorry, IS 800 also, if you go to the seismic chapter, it always say that your column capacity should be higher than the moment capacity of the beam by 1.2. So that is the concept also related to the capacity design. That means whatever the moment capacity of the beam, your column capacity must be 1.2 times of your beam capacity in case of steel structures. So that is also the concept for um, capacity, design for the steel structures. If the capacity design is nothing, like you want, only thing is what is the factor you have to take. The way you calculate the M, that remains same, whether in the steel structure or the concrete structure. The only thing is like, you have to multiply a factor here. That's all. And it varies from code to code. IS 13920 gives you 1.4. And whereas IS 800, for example, the joints, the IS 13920 say that your column capacity must be higher than 1.4 times your beam capacity. And in case of steel structures, we ensure that the column capacity must be higher than 1.2 times of your beam capacity. Yeah, that is the all other calculations, everything remains same except this factor 1.2 or 1.4.
Yes, sir. Thank you, sir. There is one more question. Please discuss something about pushover analysis, and it is used practically nowadays by Vivek Singh.
Okay, next class I'll try to.
Yeah.
Yeah.
Next session of sir is based on this performance-based analysis. So please attend that session. There is one more question, sir, from Rajesh J. How seismic mass can be compared with gravity mass?
So the gravity mass is essentially the dead load plus your live load. In the seismic mass is the dead load plus some fraction of your live load. So there is a reduction in the live load in your seismic mass, because when since the earthquake is it's uncertain, so mostly when there is a loading, earthquake loading, not necessarily your building or the structure will be fully loaded with the live load. So there is a fraction of the live load we take in calculating the seismic mass.
Any other questions? So thank you very much, sir, for your session, and hope that participants have gained the knowledge related to earthquake resistant design and related to IS 1893. Thank you very much. And again, we will rejoin at 12:15. Is it okay, sir? 12:15?
Sure. Yeah, yes, fine.
Yes, sir.
Okay,
Yes,
fine.
sir.
So let's meet at 12:15.
12:15. Okay. Thank you, sir.